Okay, we talked about using ray tracing to look at lens and image geometries. And now I'm going to do it a different way using mathematics, using the thin lens and the magnification equations for lenses to do the same thing. So you can do them, you can do this, solve this kind of problem both ways or one of the two ways. I think they kind of complement each other. So I'll let me go into this and explain it to you, and we'll do, then after I explain how the method works, I'll do an example problem, okay, to show you. Okay, so let's start off. First off, I've already put on the sheet what you need to know, or at least some of what you need to know. So the equation here on the left, 1 over dO plus 1 over di equals 1 over f. That's the thin lens equation. Okay, that's the thin lens equation. dO is as we talked about before, is the object distance. di is the image distance, and f is the focal length of the lens. Okay. The second equation here is the magnification equation. There's two of them really here, kind of combined. One is that the magnification m is equal to the height. It's the ratio of the height of the image divided by the height of the object, okay, which is kind of what you might expect. The other one, which isn't so intuitive, is that it's also equal to negative the image distance divided by the object distance, okay? So, and m is the magnification, okay? So if m is greater than 1, the magnification is greater than 1, then we have a larger image. And in that case, I call that L, large L. If m is less than 1, then we have a smaller image, and that would be an S. Okay? So there's some rules we can use to basically decide on the sign conventions that we use to determine where the image is located and that sort of thing, and whether or not the image is virtual or real. And let me talk about that for a few minutes, okay? So the quantity, the focal length quantity f, if that is positive, okay, then the lens is converging. Okay, and I'm just going to write converge here, okay? Okay, and a converging lens is a convex lens. Okay, now if the focal length is negative, then the lens is diverging. And a diverging lens is concave. And remember, I'm not speaking about mirrors here. I'm speaking only about lenses. Okay? The image distance di, if it is positive, okay, then the image is real. And I'm just going to write that R. Okay? A real image is an image that can be projected on a screen. Okay? It's an image that can be projected, either on film, a screen, or a piece of paper, something like that. Okay, it can be projected. Okay, onto a screen. Okay. If the image distance is negative, then the image is virtual, V. Okay, a virtual image is on the same side as the object. Okay? If the magnification M is positive, then the image is upright, U. Okay? And if the magnification is negative, then the image is inverted. Okay? And upright, of course, means it stands upright means just what it says. The image is upright. And if it's inverted, the image appears upside down. Oh, it, look like that. Okay, there you go. Okay, so I think I've covered it pretty well. So let's try a problem and see how this works in practice. Okay, and you can refer back to these these notes as you do the problem, or you can print this out if you like. Okay, or take a picture of it. Okay, so here's the problem. Okay, there's a magnifying glass, and this is the kind of magnifying glass that if you were, you're looking through it at a book and you're trying to magnify the text in the book so that you can read it better. So this is a magnifying glass, okay, and it has a focal length of 20 centimeters, and it's held 15 centimeters above the page of an open book, okay? So the object. Okay, so let's talk about what we have here. Okay, so first thing is that we have DO is the 15 centimeters. Okay, the focal length F is 20 centimeters. Okay, okay. Then it says, okay, then notice the focal length is positive. Okay, so the focal length is positive. So this is a converging lens. And I think if you've seen a magnifying glass, they're converging lenses, right? This is a converging lens. Okay. Okay. So the focal length is positive, so it's a converging lens. Okay. Okay. So how far from the lens is the image located? Well, first of all, let's put in so let's write the lens equation. Okay. So this is the lens equation. And I want to know how far is the lens, how far from the lens is the image located? I want to know what DI is. Okay. So first, I'm going to substitute here, right? So this is going to be 1 over 15. And I'm going to leave off the units just for simplicity. And it's going to be 1 over DI, which is what I'm solving for. Okay, equals 1 over 20. And you notice I've left off the units. Okay, my DI will be in centimeters when I get that done. Okay, so then I do some rearranging, and I get 1 over DI equals 1/20th minus 1/15th. Okay, then I get 1 over DI equals 0.05 minus 0.0667. And finally, I get 1 over DI equals minus 0.0167. And of course, I've got to solve for DI, right? So I basically, DI then is going to equal 1 divided by minus 0.0167. So DI then is going to equal a negative 60. Now here's where I bring the centimeters back in. 60 centimeters. Okay, so how far is the lens? How far from the lens is the image located? What is DI? Well, DI is 60 centimeters. Okay. I need to change that for a minute. Hold on a minute. Let me just change that. DI equals minus 60 centimeters. Okay. There we go. Minus 60 centimeters. So let's go back up and look at the table. Okay. And on the table, if DI is negative, then the image is virtual. And the image is on the same side as the object. Okay, so here, the image is virtual. By virtue of the fact DI is negative. And it's the same side as the object. So the image is the same side as the object. Okay? And so then the next question is, well, what's the magnification of this image? Okay, so now let's look at that real quick. So we're going to use the magnification formula for that. We're going to so I'm going to go M equals, and I know DI, right? And I know DO. So this is going to be a minus DI divided by DO. Okay? So this is going to be a minus 60, and I'm going to leave off units again, over DO, which is 15. And my magnification is, there are two negatives here, so they cancel. 60 over 15 is going to be positive 4. Okay, so my magnification is 4. Okay, the image is 4 times the size of the object. Okay, so the magnifying glass has done its work. It's increased the size of the text on the book by 4 times. Now, is the image upright or inverted? Okay, so let's go back to the table again. And you notice the magnification, notice our magnification is positive. It's a positive 4. So our image is upright. Okay, our image is upright. Okay, and upright is U. Okay, okay, and this thing, the 4, this means the magnification, the image is larger, L. Okay, so if I had to summarize what this image is at the end of the day, I would say this image is love. Larger, upright, and virtual, LUV. Okay? So there you go. So this is how you can solve one of these problems, and you'll have some practice problems to do.